Alright, so our last talk of the day is Tim Langen from Stuttgart, who's telling us about laser cooling of barium fluoride.
Yes, so thank you very much. Let me start by thanking the organizers for having me, and first of all, I apologize for this very bulky title. But bulk is sort of the name of the game for half of the talk, so I guess it's still okay then. But as it's already a little late, let me break that down a little bit more. So, as we heard, I will talk first about our experimental efforts to laser cool barium monofluoride. And then, in the spirit of this and the last session, I will say a few words about dipolar physics with molecules. And that is actually motivated by the experiments with, how did we say that, monoatomic molecules, and elsewhere, of course. And we've heard a lot about BECs that are just around the corner now in this field. And so I will try to give you a perspective on what's actually going on with the magnetic BECs at the moment and how we can learn something new using molecules. So let's start with barium monofluoride. So the nice thing about molecular laser cooling is, of course, that there's this large variety of species that we can get now with vastly different properties for different experiments. And barium monofluoride is now from maybe the arguably most obvious and most established group of molecules that you can laser cool. And that's alkaline earth atoms plus a fluorine atom. Where you would immediately expect to get diagonal Frank-Condon factors. And again, as we've heard today, actually most of these, all of them have at least been investigated for laser cooling or even established already. I don't think we need to talk about calcium fluoride and strontium fluoride in this respect. But we've heard already about magnesium fluorides this morning. There are people here in the audience that have thought heavily on the theory side about cooling beryllium fluoride and radium fluoride. And for radium fluoride, there's also experiments on the spectroscopy going on already. Now in Stuttgart and actually in a growing number of other places, we are interested in barium monofluoride, which, if I want to sum it up in one property, it's heavy, which sort of makes it interesting, but it also makes things quite challenging for cooling. So why is it interesting? Let me actually divide this a little bit further. So the thing is that there's a single fluoride isotope that is stable, but a series of barium isotopes, which gives us the most abundant isotopolog barium fluoride 138 and a series of other bosons. And there's also a very abundant fermions 137 barium fluoride in particular. Now, the bosons are interesting primarily as a candidate for electron PM searches. There's two collaborations working on this now. Barium fluoride has long-lived Rydberg states, actually, which have been investigated in the field group down at MIT. And we're actually talking with Ed Grant's group in trying to investigate maybe ultracold plasmas in the really truly cold translational degrees of freedom in this system. Then from a chemistry point of view, I think it's still interesting to have really this whole series of alkaline earth plus fluorine molecules and maybe be able to systematically go through all of them and investigate the chemical collisional properties. Given the many isotopes, you can of course think about isotope exchange reactions in this system and maybe also the influence of quantum statistics. That's of course very far. Also, there's this one heavier molecule, the radium fluoride, and this is of course sort of a test bed. If you can't cool this one, you'll probably not succeed with radium fluoride neither. And the nice thing, of course, is these bosons. They have a very simple hyperfine structure. So all the, I actually picked the wrong word. It's called usual laser cooling. It should work. We will see about that in the course of this talk. Now the fermions, they are very interesting. Also, due to this heavy mass for parity violation experiments, which have been pioneered in Dave's group. But they have two nuclear spins, as we heard from the magnesium fluoride earlier, which means the hyperfine structure is fully resolved and normal laser cooling is not going to work, so one has to think about new strategy. Now, creating the molecules is of course the first step, and that's pretty straightforward. Normal buffer gas cooling and ablation work. targets are pretty simple, just press targets. You have to add a little bit of calcium difluoride so that everything sticks together. The cell is just the usual imperial cell. Actually, an interesting aspect that we found out recently, inspired by Tanya's group, we used some of these macroscopic pieces of precursor material and just glued them together using Home Depot epoxy. And that works amazingly well. It gives us the most reliable and highest yields. I'm not sure if there's any fluorine in there, but that works amazingly well. Yeah, and so we end up with pretty good numbers for our beam. Also thermalization is no issue. All the cross sections in the buffer gas collisions are fine. And there's a beam that one can work with. Now, also for the level structure, it's a nice molecule. It has a familiar molecular structure. First of all, as you would expect for this type of molecule, Frank-Condon factors are, they're not perfect, but they're reasonable. It comes with very convenient wavelengths. We've heard a lot about complicated lasers that needed to be set up for certain species. Here, this is almost exactly the D1 and D2 line of cesium. So there's basically almost infinite power available from just ion lasers. That's very nice. Also, as an added little bonus, the half-time structure in the ground state is almost equidistantly split. So you would think that you just need a single EOM and you're done with addressing all these states. With this optical cycling, it's pretty straightforward and works. So we can, for example, remix the dark state and then look at the fluorescence. Of course, it goes up. Yeah, there's cycling going on. There's a few caveats though. There's this infamous loss channel that you've already heard about from YO. That is present in barium fluoride as well. So far, from what we can tell, it's not an issue, at least for beam collimation. We'll see about this once we get to a market in the future. And then there's, of course, the general properties, which are actually not as favorable as they look. There's, of course, the high mass, so that's bad. There's a pretty low scattering rate, actually, for this excited A state here. Now the wavelength is not so nice anymore because the recoil is pretty small. So that makes the cooling quite challenging. If you put in numbers, you would expect just to collimate the beam, you need a 30 centimeter interaction, which is pretty long, but so that's what we need to do. So this is what we set up with the experiment. So we start with the buffer source here on the side. Then we have this pretty long interaction region. We can just bounce our lasers back and forth and get to the transverse cooling. And then somewhere back here is the usual experimental region where we can just take pictures of our beam. The imaging, actually, I didn't want to put this, but just for them, I actually added the picture. So what works actually amazingly well, and I really want to advertise this again, is this Raman imaging, where rather than cycling on the normal cycling transition, you actually use an additional laser from nu equal to 0 to nu equal to 1, which is at 828 nanometers in barium fluoride, so also convenient wavelength. And then you can even image your molecules in a completely uncoated glass cell. So this is a picture. If you use the normal conventional imaging, the CCD camera is completely saturated. And then if you use this Raman scheme, it works amazingly well, even with this glass cell. So that's really a very nice technique. So that works nice, but you see it already here. We tried and there was no cooling. That's bad. And that's a case of don't trust any spectroscopy that you haven't done yourself. So, because I was showing you this usual scheme, which looks, except for the numbers, pretty similar to what you get, for example, in calcium monofluoride. And so we did some Doppler free absorption spectroscopy in our cell. You see 4 peaks, that looks nice, but it's actually not the 4 lines shown here. But to explain it, you need to assume an excited state level splitting of 80 megahertz. So the excited state is actually resolved. I should mention there's similar results by Boyan's group and also the EM collaboration from the Netherlands, who were also able to deduce this from ab initio calculations of the molecular structure. And there's actually even 2 more lines hidden in here that you can't see because the function ratios are too low. So intuitively, this already, of course, tells you why there was no cooling. Some lines are blue detuned, some are red detuned, and the forces are just going to go down. But if you want to quantify it a little bit more, you can put it into optical clock equations. So this is now for low magnetic fields, so it's predominantly Sisyphus cooling. You see there's a rather large region if you choose your side lens correctly, as you would expect. But if you're ignorant of this splitting up here, then flip this back and forth again. You see the range where the force is active is dramatically reduced, and also the magnitude is dramatically reduced, as you would intuitively expect. So with this, obviously, you cannot see cooling. But if you know this, then you can take this into account. And for example, Boyan's group has recently been able to do so to demonstrate Doppler forces. I say forces here and not cooling because along the way, 75% of the molecules were lost. So what is going on here? There's another problem with the spectroscopy in this molecule, and that's actually that it's quite challenging to find the IRE compass. Because, well, the bottom line is that all the excited states very strongly mix. That's not so new. That's also the case in, for example, calcium fluoride. But here, I mean, just from this old spectroscopy, they were quite far off, like 500 megahertz. That's what we learned in the end. And so with the very little signal that you expect in barium fluoride, it's just very hard to find that. But we were able to make good use of the very poor thermalization of the vibrations in our buffer gas cell, and then went through a tour de force and did spectroscopy on all of these lines here, for all the rotational and vibrational transitions for all the isotopologues. Here's just an example. I'm not going to go into the details, but the bottom line is that you can now have new molecular constants for 138 and 136 barium fluoride, which are basically just limited by the precision of our wavelet. And the analysis for the fermions is actually ongoing. There's probably also something wrong with the hyperfine structure in the excited state, but that is so complicated that you probably need different methods to actually extract it, rather than just direct optical spectroscopy. Yeah, we also looked into this delta state transitions, and just as in YO, it's very, very narrow. So there's a prospect for narrow line cooling there as well. Good. So yeah, all the parameters are available now. So the guys are now working in the lab to get the full laser cooling without actually losing the molecules. But in the process of doing that, of course, it's still going to be challenging. And one important question is, how do you actually set the sidebands now? So here's a picture again of this spectroscopy that I was showing you, now indicating also all the lines that are there. And so the problem is, of course, that they all overlap. So if you just, for example, blue detune to get some nice Sisyphus forces, that is not necessarily the best choice. What the optical clock equations tell us is that rather you want to use less sidebands, and then basically drive everything that is not a strong transition off resonantly. Now we can argue about what kind of molasses that really is, but I mean, I'm not really showing you this for the bosons, but the point is this is a general principle. Basically, in the end, you're reducing some undesired coherent resonances that show up in resistance forces, but you can apply it to the fermions as well. So, as I said, the fermions, they have two nuclear spins, which give you this very pretty hyperfine structure here. As in magnesium fluoride, you get basically a doublet here now, which is in this case separated by about 4.8 gigahertz. So you need to add one additional laser. That's still reasonable given that it's all just diode lasers. You can just offset lock them or something like this. But then there's still a lot of lines. There's 48 ground state levels, 16 excited state levels, and 22 transitions between them. So that would still be a lot of sideband. The nice thing though is that this usual cycling transition should still work in barium monofluoride, in contrast to, for example, YBOH. There is no hyperfine mixing in the excited state that would break the Paradis selection rule that produces the rotational closure. So that should be fine. But so, there's still these 22 transitions, but the point is that you can do as I just showed you for the bosons. You can just address a few of them. stripe the others off resonantly so that you don't get dark states. And then actually it turns out that you can still get very large forces because the ratio of excited states to ground states is pretty much the same as in the bosons. And just as an example, for beam collimation, in an experiment like the one that Dave is running, you can collimate the beam. So this is a beam source here. In this experiment, you need to get this beam through a very long magnet. And now just using 4 lasers and 112 levels in total, you can basically collimate this very well. So it's basically one recomper that you need to address. So that looks pretty reasonable, and of course we're going to try this as well in the near future. So now let me switch gears actually to dipolar physics again. And as I've said, this is motivated by our monoatomic molecules. So I want to contrast these two real quick to bring us all on the same page. So the atom that we're working with in Stuttgart is Bose-Einstein, which has of course a fixed dipolar strength because the magnetic moment comes from the atomic structure basically. And I'm always converting this into this length scale here so that you can nicely compare the molecules and the atoms. So in this Bose-Einstein, which is actually the most magnetic atom we have in the periodic table, this is like 130 Bohr radii. Of course, in molecules, the whole selling point is that this is going to be bigger, and it's going to be tunable by external electric fields, for example. Now, the other advantage of the atoms is, of course, that cooling is pretty straightforward in comparison to molecules, and they're collisionally stable. So it's pretty easy to generate these nice bulk BECs that we like to work with. And what I would like to tell you is really just working with the bulk, there's a lot of interesting things that you can do. Of course, for molecules, the cooling is still a challenge. There's inelastic losses, there may be chemistry that needs to be addressed. The other important thing in the atoms is that it's short-range interactions can easily be tuned using Feshbach resonances. You have just seen the case in erbium. There are a lot of resonances in this protein as well, but you can always find one that you can tune stuff very nicely. This is, of course, another issue for the molecules that needs to be addressed. But the point is, just based on this, in recent years, there was a lot of progress in the description of these BECs. There's a lot of many-body physics that can be explored, and importantly, there's beyond mean field effects that people thought are not important, but they are important, and no one has applied these to molecules actually so far, because people just thought it's funny. No one has produced a molecular BEC, so no one did it. So, but of course, there are now all these very nice new developments which really address these issues. We have now degenerate gases, so far it's Fermi gases, but of course, all this progress that we've seen here already in molecular laser cooling, and I'd like to add actually something to the plot we've seen this morning with this very nice increase in phase space density. So this is now the full race to absolute zero, including cryogenics, starting in 1880. And you see there's sort of a Moore's law here. So along the way, there's quite a few Nobel Prizes in condensed matter physics. And you see how cooling of atoms really changed this game. And then I'm very happy to present So I think we're getting there. And then we're getting there also in terms of these collisions. There's basically the DC shielding that we discussed already, and microwave shielding, where always the bottom line is that you engineer some kind of barrier that gets rid of all the short-range physics of evil. And so with this, it's really now a point where you can check in the tools developed for magnetic atoms what is actually going to happen if we produce a molecular Good. So now the main focus of that field at the moment are supersolids, not super duper solids, but supersolids, which is, just to bring us all on the same page again, a very counterintuitive and strange state of matter that is both solid and superfluid at the same time. And I really mean this as the quantum superposition here of two phases of matter. So people have been looking for this for 60 years, and there's basically two perspectives on this. There can be vacancy-induced supersolids. That's asking the question, can a solid be a superfluid? Or you can come from the other side and look for droplet supersolids, which asks the question, can a superfluid be a solid? So the picture here is basically that you have a solid and there's holes in this solid, vacancies that can fly around and delocalize and then Bose-condense. So this gives you a finite superfluid fraction. And people thought this is realized in helium. There's a long story. People have been looking for this. They thought they found it and they didn't. So it's unclear basically if this exists in nature anyway. And then you can have a superfluid which needs to break some kind of translation symmetry. And this is nicely illustrated in this little experiment that you can do at home as well. This is a classical ferrofluid that we're exposing to a magnetic field here. And you see it breaks translation symmetry. So that's the Rosenzweig instability of classical ferrofluid. Okay, and it turns out, I mean, this is obviously not a supersolid yet, but the quantum version is realized in ultracold atomic gas. So, how does that look like? You basically start from a VC, which is a smooth thing that sits in some kind of trap. Then you make the system more dipolar. You cannot tune the dipolar rate, but you can change the contact interactions. So you make these smaller, and then you make it more dipolar. And you end up in this kind of classical crystal, very much like the ferrofluid. And that's exactly where these new theory descriptions come in, because normally on a mean field level this is not stable. You would think it explodes. And you need a very fine-tuned balance between contact interactions and dipolar interactions for it actually to be stable. And somewhere in between, there's even more fine-tuning. There's a very small region of interactions where you see there's really this superposition of the two aspects. You have a superfluid thing still in the back, and on the top there's some sort of very small but still crystal emerging. And I mean, we did this in the experiment. It looks exactly like this. There's a lot of things that you can map out on top of this, but they're not very interesting right now. Coherences, you connect elementary excitations. You see this kept as busy. There's also important work here in Wolfgang's group at MIT that I should mention, and of course in Innsbruck and Pisa on this dipolar systems. The bottom line is this weird state of matter does exist. But now the problem is, it turns out there are actually a lot of questions that we cannot address using magnetic atoms or helium for that matter. And of course, I'm going to argue that molecules are like the best thing that you can do to this. The first thing is you can calculate a phase diagram for this. And it turns out you don't just find these droplet supersolids, but it gets even weirder. You can also find these honeycombs. And this is connected to something that is very similar to if you have a water drop. You cannot compress the water indefinitely. At some point, the van der Waals repulsion is going to limit the density that you can achieve. And something very similar happens here. So if you increase the density, at some point it becomes energetically more favorable to actually fill the holes in between the droplets. And that's why you get this nice pattern. It turns out there are even more patterns that you can get, like stripes or labyrinths or pumpkins. So it's very rich. And then you can calculate the phase diagram, and it looks like this as a function of particle number and contact interaction strength. And these are now parameters for this problem. And the problem is, this is the region you can currently access with atoms. You cannot reach these very nice and interesting states. But now you can actually exploit a symmetry in the description of these dipolar systems, where it's somewhat similar to increase the particle number or to increase the dipoles. And this, of course, you can very easily do. So you see this is just a moderate increase here. But then all these phases, as you would expect, move on to lower particle numbers. Why is this interesting? I mean, not only because of the new states of matter that you can now reach, but this is a whole field that people spend their careers on looking at pattern formation. And you see the very same patterns here appear across very vastly different energy and length scales, from animal skin to the strongly interacting matter inside the neutron star. So it's quite interesting if one can realize this in an experiment. Of course, for this, you need shielding and fully tunable interactions. And so our approach, we teamed up with Gulman Kimener for this, was also microwave dressing in combination with electric fields. I mean, you've heard about this already. The bottom line is, as you increase the microwave dressing, the shielding works. But then if you go a little bit further, you're actually creating a shallow potential well, and there's bound states in there that can give you scattering resonances. And for example, for BEC, you would work somewhere here, for example, and then have fully tunable interactions, and you get rid of collisions, chemistry completely. And then you can add some perturbative DC field on top of this and easily tune to the values you require to explore the space diagram. So this gives you sufficiently tunable molecular gases. I'm not saying this is the only way to do it, this is just one way to achieve this. And actually, the experts might say, okay, these are really tough and strong microwaves here. But if you don't want to get to these high fields, then maybe you go with Theis's suggestion and make the circular polarization a little bit elliptical. And then just this week, Theis and Manuel Bloch's group have realized this in sodium potassium tunability. Good, I'm going to speed up a little bit. So there's another example in the strongly interacting unit. If you make the dipoles really, really large, then you get, again, something fundamentally new. I told you about this saturation density. And that keeps decreasing as you make the dipoles larger as in molecules. Yeah? And at some point, you end up with just one particle per lattice side. So you're basically creating a self-assembled crystal with unit filling, and that should also have supersolid properties in it. So this would be the transition to this vacancy-induced supersolid. So in a way, there's this limit here that is maybe realized in helium, but no one knows. Then there's these droplets, which all contain a lot of atoms, realized in magnetic atoms. And dipolar molecules should really give you a comprehensive picture of this state of matter that people have been investigating for 60 years. There's many more things that you can investigate. In particular, one thing I want to mention is doubly dipolar supersolids. So if you have the magnetic degree of freedom, as in the laser-cooled species, you can play with this as well and have another degree of freedom, more states of matter, more stuff in the base diagram that people have already investigated. So we're also joining this effort to make a Bose-Einstein condensate with the usual molecule. Obviously, barium fluoride is not something that this is going to happen in the near future, as the lead times for lasers and vacuum equipment are actually quite long at the moment. All I want to say about this experiment is that, of course, microwaves are going to play a big role. And we've come up with a little bit of a design inspired on the one hand with the DC geometry that is used in GILA in the KRB experiment, but also with the little antennas that are used to manipulate NV centers, and so this should all go into the vacuum to really reach these very high microwave dressing Rabi frequencies that you need to explore all of this. And I mean, this is an ITO-coated glass plate as in the GILA experiment, so you should still have optical access and then do all the fancy stuff. So we will see, yeah. Good, so I come to my conclusion. So I've talked about laser cooling of barium monoploid, which is a challenging species, as I may have convinced you, but cooling is making progress in many labs now. And in particular, the strategies that we've come up with should work both for bosons and for fermions. That will be interesting to explore. And then for dipolar physics, my take-home message is really that shielding alone is maybe not enough, but you really need also independent tunability of the interactions. If you really want to do dipolar physics in the BEC, this can be realized, for example, with microwaves. But then once you get there, there's really exciting new insights that you can gain. There's really fundamentally new stuff that you cannot do with the magnetic condensates. Okay, yeah, if you're interested in supersolids, there's a review that I wrote for Physics Today. And with this, actually, I show you the people that are doing this in my group. And for the TRISA people, maybe as a last comment, if you are waiting for your objective or something like this, you can also directly print this onto an optical fiber. So if you're interested in that, talk to me afterwards. Okay, thank you very much.
Questions?
I think you said that in the fermionic barium fluoride, the excited state hyperfine structure doesn't destroy the rotational pleasure. Is it just the excited state you looked at, or what about the ground state?
Yeah, in the excited state there should be some, I think it's some lambda doubling terms that basically bring you into the, I think that's the case in by the old age, right? I see you nodding, yeah. And then you basically end up in the wrong rotational ground state in this way. In the bosons that's never a problem because it's very small, but in these fermions it can be quite substantial. But it turns out in barium fluoride very, very small, and it should not be a problem, at least on for collimation.
But you also have this large hyperfine structure in the ground state, which is not so different from the rotational interval, right? So I wonder about the hyperfine mixing induced
Should
leak.
not be a problem. Well, if the constants are all correct. So this is of course still pending updates on the spectroscopy, but should not be a problem. And you always, in contrast to, for example, slowing in calcium fluoride, you're always going to use both excited states, because then the ratio of excited to ground states is actually more in your favor, and you get larger forces. But when it should cycle, we will see.
Any other questions? All right, well, let's thank Tim again, and let's thank all the speakers for a great day.